Okay, so you wanted to, in the title of the live stream here is space-time groups. So what is that connected to? Is that connected to our work on Lorentz lattices, or does that connect back to the history of physics episode you just did, or is it more?
Yeah, it can connect to Poincare group. Right now, I believe when you can correct me if you're wrong because you work more on that than me.
Okay.
Laurentian group is more on space, whereas Poincare group is more on space-time, the relativity things like that. I think it's more accurate. So you need a Poincare group, I think. That's my feeling. I don't know much about that. You have worked more on that.
Yeah.
But the Laurentian group is more attuned to space than space-time. Whereas
I don't know if that's correct, though.
Group,
it seems like the Lorentz group is a subgroup of the Poincare group.
Yeah.
So I'm pretty sure that the Lorentzian group is all space-time
you can?
transformations. Yeah, that would necessarily include space and time because they're Lorentz transforms, aren't they? Of space-time, maybe.
Yeah, but are there limitations? My point is that are they more limited than Poincare group in terms of?
Yeah, they are, because the Poincare group,
yeah.
like I said, the Lorentz group is a subset of the Poincare group. So it's actually it's half the number of transformations as the Poincare group. So the Poincare group is supposed to be isomorphic with the GL23 group. So yeah, and then whereas the Lorentz lattice group is supposed to be isomorphic with the SL2C group, I think. So, and two of the SL2C groups fit in the GL23, general linear matrices of 2x2 matrices with 3 elements, because they're mod 3. So they also have another name, which is to do with the binary octahedral group. But so that's kind of what part of the research I've been looking into is about. Applying those matrices to what do you call those things again? Lorentz lattices. So if I have that notebook, I can open it. So basically, I was working on that remember we were doing work on that here, and I found that's not it, or maybe that is it. Yeah, that is it. Sorry. So okay, I'll just share my screen. Oh, it says error loading the notebook. Come on. Seems to be a bit of a problem with loading it. Anyway, so it doesn't really matter. Hopefully some of these others load. Let me just check. Okay, none of these really seem to be working. I might have to switch the other computer if this is going to be an issue. Should have tested this before we started, but that's life. Oh, here we go. Here's another one. Yeah, it's all the same problem with them. Let me just see if there's another way to go about doing this. So with the Lorentz lattices, anyway, I was able to do it discretely using this process, which is called the Arnold. I think it's called the Arnold cat method, Arnold's cat, and that works fine. But as we saw, it just, we had the 3x3 order square, and then we had the different points colored with different colors, 1 to 9, I think it was. Yeah, and then we'd apply the Arnold's cat transformation using like matrices from the Lorentz group or the Poincare group, whichever, and then it would just reorder them in a specific way, and that was fine. But to understand how that ordering was coming about and whether all of them could be real world Lorentz transforms or lattice transforms, it was necessary, we thought, to do a continuous transformation so we can actually see the points leave the space and come in at different other points and see how they reorder themselves. So my method for doing that was to just transform them without any kind of modular consideration, which is how the Arnold-Katz method works. It would take the box and then it would stretch it, and then the bits that are sticking out, it will just paste them back in to where there's missing parts because of the stretching has occurred in the original window, and then it'll stretch that and keep doing it over and over again, and that's fine. But in order to do it continuously, I was thinking of kind of doing the same thing, but we have to know how the sides of the domain, fundamental domain, reconnect with each other. So it appears that let's say the top right-hand corner is identified with the top left-hand corner, meaning that anything that goes out of the top right-hand corner comes in at the top left, and vice versa at the bottom. So that's kind of non-trivial for me anyway, because it's specific rotation. Now there's other, I have worked on other things where you have that kind of modularity where something leaves one side, comes in the other. So perhaps I've already solved that, and I can just look at how to sort of modify that work so that we can get to the point we want to be at. But I don't think we're going to do that today because I'm not set up for that. But we'll see how we get on, if any of these notebooks work, and then if not, I'll have to switch over to the other computer anyway. So yeah. Is there any other topics you wanted to discuss?
Yeah. So one of the things, the history of physics in the last one, where you couldn't be there, but I think you have seen that, right? The video that I had.
I watched it.
Yeah. So in that one, I bring out the more from the historical point of view, the facts rather than my opinion and things. So that's something we can base on all the time. And we went through it 2 weeks ago. Of course, most of the things we went through it. More than 80% is the same thing that we had discussions. So the main thing I am finding, and I have sent out a publication, which kind of more on the rank 6 tensor for the time, but in that one I compare the rank 4. You remember rank 4 tensor I already have published in or JPS. We went through that conservation and all those things.
Yeah.
So that I did a transformation, and I find that it has 4x4 matrix, and it is analogous to the Schwarzschild matrix. So that's something I find that, yeah, it's interesting. So what I find is remember we are talking about quantum mechanics and the relativity, and see how they were trying to do with each other because they're contemporary physics that Einstein and Schrodinger and Bohr, other people were doing. So it's a simultaneous thing that was happening with the Planck and all. And Einstein himself, when he find his photoelectric effect, he was in a way hinting on the quantum mechanics, the quantum aspects, right? The photon and things like that. But he had a lot of problem with that's one thing I am looking at, locality and the non-locality. So right now, I mentioned about quantum form, right? And you mentioned that people were trying to do the wormhole and everything, it doesn't work. But I think you had to, so I'm coming with a model, and I wanted to put that graphic in the paper, but I didn't put that because I'll see. I mean, when they review it, I may add that. I have one graphic. I think I can show that maybe.
Yeah,
I can show that briefly. What the overall it's a kind of a picture. I see. So let me see. Let me try to pull up that. Hopefully it'll show up correctly. I don't know whether you can you see that?
Hang on a sec. Yeah, I can make this more. I can make it bigger.
Yeah.
There we go.
I don't know whether I need to. Can you see the whole entire? Let me see.
Yeah, irreversible something.
Yeah. So
Micro
let
black
me
holes.
explain that. Yeah. Let me explain that. So I think, and this is a very simple sketch I'm doing.
Yeah.
Uh, so you need more graphics, but that's one line. And the quantum form is like electromagnetism. Like ether or vacuum that spreads almost infinite space, almost, right?
Right.
So that is, I think that's non-locality that explains, and you can describe a certain wave function. And uh, I will come to the irreversible micro black holes later on, but that's one of the things. So the gravity, on the other hand, is like a vacuum bath, and people are thinking about it. I saw a couple of videos. People are thinking like Higgs bath or vacuum bath. That's locality. See, gravity, and that's one of the things that come like Newton said that gravity is just force between two objects, but Einstein said as no, it's the matter bends the space time or curves the space time, and then the space time then creates that gravity effect. So it's not a force per se. So, but it's whatever it is, it's local. The gravity is local, and that's very important. So there's a locality in terms of quantum mechanics. If we say talk about quantum gravity, it's a local effect. It's not a global effect. Whereas the quantum form or the electromagnetism is a global thing. So that's the main thing that I come. But how they commute with each other, that's where they finally connect with each other, see, in a fine structured manner. And that's because I call it this area that connects the gravity with the quantum form. The vacuum bath with the quantum form is the superluminal Planck like fine particle field energy structures. So they are even our brains may be like that, but so that each time the locality commutes with the non-locality, or the non-locality tries to commute with the gravity. So they commute with each other. But they can, which means that they can commute, but also they can also disconnect at some point. I think there are evidence that show we can actually bring out that. Also, our multiverse things that we are talking about. That's why our research may be very important about your 4D hyperspace, and then rank 6 time tensor may be important to understand this and maybe go very well with that. But this is kind of a conjecture or concept that I have of the overall picture. So the electromagnetism is separate from the gravity. They mix only by this process, by some fine structure process, uh, and they connect with each other. But they can disconnect also. Uh, and why is the reversal micro black holes? It's little more involved. I was thinking about under reversal micro, which means that I think there are two types of black holes. Where so right now people initially Hawking's idea was that the black holes they switch off, right? They switch off everything. The light goes in, then the light cannot go any further. So we don't get any information. So there is a disconnect of information. But later on, Hawking said there is a radiation that comes out. So the information is not lost. It's not one way information in the black hole. So the concern. But I think right now I'm just working on it. That's a conjecture that there are two types of black holes. One is where the information goes in, doesn't come out. One where reversible, like Hawking radiation. You can get information from them. And I find myself, I did some thought experiment. I did some, mental experiments, and I see that I use the matrix protocol, and I see that, initially I get some information, communication. Then I connect, I store it in certain way using like inner product, outer product type of thing. So it's very logical way of storing it. Then I try to retrieve that. Some of the information I can never retrieve. So they're reversible. No matter I try, I can. But some other information I can retrieve. So I think there's a real sink, which is irreversible sink, which I call it irreversible micro black hole, actually exists because they become part of the whole noise. I believe the whole thing is noise and it's lost. It is deconvoluted there. So you cannot never retrieve it. But there are other type of information if we use the proper logic technique that we can retrieve them. So that's what I believe. So there are two types of micro black holes. That's an interesting thing. The black holes which connects to eventually the black holes themselves. But it may be working at the micro black hole level, like at the quantum level or Planck level. But the larger scheme also, they could be black holes which may not have Hawking radiation, and other things which may have Hawking radiation. This is what I come up with as a general conjecture to explain the electromagnetic. I call the electromagnetic gravity. It's not completely unified because I have not brought in the idea of strong nuclear or weak nuclear. Maybe we can later on build into that, but this is essentially electromagnetism and gravity. How they, because they are the big things, how they connect, how they lock. So the locality of the gravity is very, very important, I think, because very similar to what Einstein said. It may not be exactly like that, but the matter, where does the matter come from? So that's the big problem, right? Once the matter comes from, then it curves the space time, and the space time now decides. Okay, I mentioned that. Now the space time says, now it's my turn. I'm going to tell you how you are going to move the matter. So once the matter curves the space time, the space time now takes over and decides the equation of motion. How that matter or the object is going to move. So, like Wheeler said, I mentioned like the Wheeler said, his famous quote about the about Einstein's general theory of relativity of gravity. So that I think that seems to be okay, but I still believe the the gravitational speed is instantaneous, and the light speed also. There's an instantaneity that we are dealing with. I think that's something we have to reconcile to, in this set. That's what I'm trying to do. So will it maintain the instantaneity? Because I think gravity, of course, and then measurements also show the gravitation field, whatever, is many orders of greater, faster than the speed of light. But the gravity itself may not be that fast. The bending of the space time and things like that. But there is a wave. The gravitational wave is in the range of speed of light. So these kinds of things are kind of happening. So, but in terms of particles, I believe I call them excitons are part of the quantum form. They are the ones who are commuting that, whereas the gravity is graviton, like we say, graviton. So in terms of particles, you have excitons that commute with gravitons. And I believe, and my in this present paper I'm sending out, which is under peer review, is the graviton acts like a gradient of the field. So if I write this, it will be like graviton will have a gradient. So it's the gradient of graviton. And then you have so this is the gradient or ket vector. Whereas the excitons will have uh, their own, exciton is the Bra vector, the wave function. So these two interact somehow. These two interact, and they produce the overall Gij matrix, which is like, I mean, it's extended form of Schwarzschild metric. So, but the extended form in the sense that Schwarzschild is 4 by 4, but this will be higher. So I was trying to do, now I'm trying to work out this aspect, what Schwarzschild was trying to do.
Yeah.
And it's kind of a little bit complicated. The Riemann thing as R alpha mu nu, it's not well written here. So let me write down.
When you're saying Schwarzschild matrix.
Yeah, it's 4 by 4, right? Matrix is 4 by 4, right?
Well, it would be, wouldn't it? Because it's space-time matrix.
Yeah. So if I can pull up that,
they usually refer to it. They usually refer to it as a metric.
Metric.
Be a spherical coordinate. Okay.
So,
essentially, it's the black hole thing, is it?
Yeah, black hole. So here you have the black hole, 1 over whatever the 1 minus G something, and so this gives the R square, that gives the matrix, and this is the one that is creating the black hole, right?
Yeah.
I'm just putting a
Okay, so
that,
yeah.
So what happens in this case? What I'm talking about is. What I'm talking about is the problem with Einstein when he went to Ricci is that he started with the Riemann, which says that alpha mu nu, something like that. This is the Riemann tensor.
Right.
Riemann tensor. But then he had converted to Ricci tensor, right?
Okay, at this point, you're kind of losing me. Yeah. Why is it converted to a Ricci tensor?
So if you look at the Einstein equation, right? Because this is rank 2, but it has this tensor, you cannot describe how exactly this tensor is. So essentially what is happening is that you have Riemann tensor is very general curvature, right? It talks about a curvature. It's a general curvature equation. It's a geometry, right? General curvature geometry. These are Riemann tensors. So Riemann says that R mu nu is, let's say, 2 coordinates. Let's say mu is like that. Mu is like that. I'm trying to simplify it. It's more complicated than that.
Of course.
But then alpha may be something that angle that connects them. Okay. So he's come up with, because he says that you can do like a Pythagorean thing. I'm simplifying Riemann. Okay, it's much more complicated than that. But this is where I interpret mu nu. It could be a vector, imaginary vector. And then you have a scalar. Then you have a scalar, which is like So I had to change it. I had to do like something. I had to put it there, not the
Yeah,
thing.
well, I suppose. Yeah, I mean those angles are only angles because of the deformation of the metric, right?
Yeah. In any
Yeah, but where
any
does the Ricci
geometry.
tensor come into it then?
Ricci tensor simplifies this, uh, makes
Oh,
it simpler. So it's pseudo Riemannian and things like that. Okay. So the way I am explaining is, which is,
okay,
we have to go back to the original definition, but I'm trying to loosen it. I'm trying to make it a simpler
okay,
explanation. So this is what Riemann saying. So when you do this, Pythagorean says that this one will become R alpha. They combine together. The scalar and the vector comes together, and
okay,
they create. So they become complex variable, complex tensor. So this is a very simple way of looking at. So Riemann was trying to say, okay, this has a vector aspect and a scalar aspect, but you can combine them together and give you like a tensor. Okay, that's the simplest way. Now the Ricci came, the Ricci tensor came and did the following. He was trying to simplify it, and he said that suppose uh, I have this vector and scalar. I can I no I can split it. I can split it into two aspects. Um so one is scalar, one is vector. So uh, let me rewrite that. I was thinking very high, trying to simplify that. Uh,
okay. You need to move the page up so we can see it.
yeah. So Ricci tensor is where you have the scalar, right? So it's something like this. Let's say start with that. So
Okay,
now I can write R new, and I had to put something here to make it different,
okay,
or RG or something here. They're not the same things. And then I can split it up into uh, IR mu new IR plus a scalar. So this is another thing, and the scalar, let's say like that,
okay.
are alpha. So this splitting is one of the key aspects for Ricci tensor. As you know, in Einstein equation, you have a scalar tensor, a scalar value, as well as a as well as a vector value. And the actual
An
Einstein
imaginary
equation,
component. But wait a second though, because didn't you just say earlier that the Riemann tensor is a complex number?
yeah, this is the one. Now we can split it into
Yeah, but a complex number is just the combination of a scalar value and an
vector
imaginary
value.
value multiplied by
Yeah,
a scalar. So it would be the same anyway. That's still
no,
a
no.
complex
But
number.
now, in terms of the matrix, how do you write this matrix? Very complicated. But in this category, you can do, let's say mu is varying from 1 to 4, right? And mu is varying from 1 to 4. I can write a simply a 4 by 4 matrix, right? So I will have R 1 1, R 1 2, so and so forth, right?
Yeah.
Up to R 1 4. And I can do R 2 1 like that, all the way up to R 4 1.
Yeah.
And I can go all the way to R 4 4, right?
Yes.
This is essentially what quadside thing is, in some sense. But then I have one more. I have a
Oh.
scalar value here.
Oh,
Okay.
okay.
It may be something like this. Let's say R1, R2. I know it's R2,
Oh, yeah, yeah,
R3.
yeah. Okay, so
Alpha, let's say alpha.
so one is a vector and one is a matrix.
One is a matrix, but it is scalar. Scalar here, matrix.
Well, no, the scalar one there is a vector, isn't it?
Yeah, scalar, but yeah, that's the thing. I think I have to look into that. But how exactly? So it may be
Well, it looks
working
like a
like
column. It looks like a column vector. So you're saying
this. It
maybe
could be like this. It could be like that. So it will.
well,
It will
that's
be.
just a row vector then.
It's a row. Yeah.
It's a row, but it's still a vector.
Yeah. So that's the transformation. So they're trying to convert it.
So one is a matrix. The other one's a vector. But so you've got plus there, right? So what happens when you add? Shouldn't it, usually when you do like matrix multiplication, like how do you add them together? Do you just
yeah. So you need another unit vector here, some kind of a unit vector. What you call you know, you have to multiply by unit vector to make it compatible. You see that? So you need something here.
So you'd multiply a row by a column vector, is it? And then so then you could add the two matrices together?
Yeah. So in order to do that, so that's the complicated thing, right? But they worked out a way to do that. So I'm saying that where the problem is coming from, you see that?
Yeah.
It's not a simple thing. That's what I'm trying to say.
It's not too difficult either.
Yeah, but there is a way to do
once this. Once you add the two together, you wind up with a complex matrix. Is that it?
Yeah. So that's the idea. So that's where the metrics come into picture. The metric came to take care of that. The metric aspect came. That's why G mu nu. You see that G mu nu came into picture to take care of that. That's what Schwarzschild did. Clever way, very smart way. So the G mu nu is a huge matrix. You see that people are still figuring out, and it can become very huge. Like Sean Carroll, if you see his video,
why would it be so big? It only has two indices.
Yeah, but when you talk about, you have to see Sean Carroll's video that how he computes the metrics. Then he says that as a graduate student, he had to do that.
Well, do you have the Sean Carroll has a lot of videos. Do you have a link to it?
There's a particular one. I have. I think I don't. I may have pulled out. Let me see.
Okay.
I may have pulled out. I don't know whether I kept that. I wish I had, but I may have it.
Okay.
Because there are too many things, you know. But I found that very informative, very useful.
Right.
Sean Carroll's thing. Because that gives the sense of the trying to pull up. I wrote it somewhere. Let me check. I may have. Did I put it somewhere? Sure, if it is. Let me think 1 minute. Sean Carroll. Yeah, that's very useful. If you cannot find it now, next time I'll just bring it up. But let's see.
Sure.
It because it connects nicely. You know.
Absolutely. Yeah. No, I'd be interested. Like, you don't have to find it now, but if you, when you do find it, send it on to me. Like, email us or something.
Yeah, I will send it to you. But essentially,
I can add it to the description of the video as well if necessary.
Yeah. Okay. Yeah. So I will send to you because I don't want to spend too much time. We have only like another 10-15 minutes.
But, no, that's no need. That's not. Yeah. It's just if you had it in hand. Otherwise, let's move on.
Yeah. So what he says that the matrix is highly complex, and he says he has put out the actual matrix, which starts becoming huge. You know, so the computation becomes big. But essentially, what they did was they transferred all the information on the metrics, the difficult things, So they separated it out. That's how Einstein's thing came into being. And let me see Einstein's equation. Uh, I think it is in my previous thing, so it will be. I'll just write down Einstein equation, the relativity equation. Uh,
The field equation.
The Einstein equation is
Was it like or mu nu or something, and then?
Yeah, that's it. But let me see. Oh, how did it gone out? Kind of removed Einstein equation here. So it's strange. What happened here? Anyway, I can pull up easily. Einstein. Einstein field equation. I remember it offhand. I cannot. I usually remember it, but I cannot. I don't want to make a mistake here. Okay, yeah, it is the Einstein field equation. So Einstein field equation is G mu nu plus lambda G mu nu equals K times. It's a general equation where one of them has a Ricci tensor. You can express that in terms of Ricci tensor, and G mu nu actually is equal to R mu nu, which is a Ricci thing, minus 1/2 R G mu nu. Okay, so this is your R mu nu is a Ricci curvature tensor.
Okay.
And the R is the scalar curvature. Called the
Okay, but so let's say you apply that to the Earth, yeah? You've got T mu nu, and then so that would be your energy density equation.
Energy stress tensor.
Divided by energy divided by volume or whatever. And then, the stress energy tensor. And then, so you could do it simply, you just energy divided by volume. But so then that's the planet Earth. And then you have the curvature of space on the left-hand side then, I guess. And but then you have this cosmological constant in there.
That's where the problem came from. And people think that Einstein did a blunder.
Just one minute before you go there, because I'm sure that's going to be interesting. But why would you, like in a local region of space where the Earth is just curving the space-time, why do you need the lambda constant? Because it's not going to it's not going to really do anything, is it? Because that's only for large-scale stuff. But that's one point. But then let's assume that we are dealing with a large-scale volume like the entire universe. Then we would expect that the combined gravitational force of all the objects in the universe draws everything together. But because of the cosmological constant, space is expanding. So that, how do you say that? It kind of repels everything. So it prevents everything from collapsing into a black hole, right?
Yes.
Would you agree? Okay, but what if that's wrong though? Because in the well, I mean, it could be right, but I'm just speculating. What if it's wrong in this from the point of view of the anamorphic universe model? Because in that model, there is no expansion of space, right? Just the redshift is just a kind of an illusion generated by the perspective projection, stereographic. So, and also the structure of space is a kind of a hypersphere. So now, obviously, gravity is still a force across the hypersphere and across everything else, but we don't have a. So, what's preventing everything from collapsing in that universe? What maybe we do need the cosmological constant then.
That's what Einstein came up with. So Einstein came up. Why did he come up with the cosmological constant?
Yeah.
Because he thought that if he does not have, he'll have a. It will just explode. There is no containment.
Okay, fine. So I have no problem with that. Seems like a reasonable thing then. But then you have to ask, well, what is the energy driving that? Because like, if it's an expanding universe and it's accelerating, then you have the dark energy factor. But even if it's not accelerating, you'd still need some energy to produce the counteracting force, right? Okay, so you might still need dark energy then, even in the anamorphic universe model, even though the universe is not expanding in the model.
Yeah.
Okay. That's good to know. I was thinking that we might need to do away with dark, or that it was being eliminated, but by the sense of it, it would still be there.
I'm still thinking about it, but I think what I showed you, the picture of quantum form and the vacuum bath, commuting with each other, might solve even the dark matter interaction. But of course, it's just too much of a conjecture. But it's kind of, I'm thinking aloud about that. I'm not sure.
Okay, that's fine.
I have to work out.
So what exactly? So what kind of point? Like, what point are you making with all of this? It's very interesting, but like, how does this? How are you connecting all of this up to what you're talking about, or is there?
Yeah. So I'm saying that why we need to consider, for example, time as not just scalar time. Why we need tensor time. This is my eventual explanation, because right now nobody has come up with the idea of tensor time, but I am coming with the idea of tensor time, so I had to justify why you need a tensor time. You see that's the fundamental thing. People are going to question, why do you need a tensor time? So I'm coming with a very rigorous way of explaining that, why we need a tensor time.
Okay, and do you have you solved that yet, or?
Yeah, actually, in the present, one of the papers I sent out for peer review, I started looking at that, and then starting with like comparing. One of them is similar to Schwarzschild metric, so it means that for the rank 4 is very rank 4 time tensor with the gravity as gradient will commute with the Schwarzschild metric. Now, what I see the next step is why we need the rank 6. So for me, that answer comes from the idea group theory and things like that. And also, when you describe, this is where the Riemann tensor, that I believe that larger scale, you have to go from Ricci tensor to Riemann tensor. Because we have to talk about general curvature. Ricci tensor it's a simplification or assumption. And even Schwarzschild did this. He assumed that it's a vacuum. He solved for the vacuum, where R mu nu equal to 0. That's how we came up with this metric. So the question is then, it's the fluctuation in the vacuum that's creating that. And then right now, people think that fluctuation can lead to vacuum bath, which creates gravity. Now they're not be able to prove completely. That's because something is missing there. And something is a time tensor. I believe that something is time tensor. Now I'm coming into the picture that when you talk about time tensor, you have to talk about the rank. And I'm looking at the Wikipedia. If I don't know whether I can pull up that. Let me get up. Let me try to pull up my screen here if it's possible, and I'll show you what I'm seeing here about Einstein thing. So let me. So I have to get off this. Okay, so now let me go here. Can you see this now?
Yeah.
So this is the, you can see, right, what I'm showing? Okay.
Yes.
This is the Einstein field equation, right? So now we have the Einstein general relativity, G mu nu, the lambda, G mu nu, that's the equation. And then it says, explains what G mu nu is R mu nu, which is a Ricci curvature tensor, what I wrote. And then R is a curvature, and the G mu nu is the metric. And then K is that 8 pi G C to the power 4.
Mm-hmm.
Then you can write everything in terms of Ricci tensor like this. R mu nu minus R. So that's Einstein, the whole equation.
Right.
Now, when you come back here, G mu nu has this kind of formation, diagonal terms and all that.
Yeah.
And the interesting thing here is equivalent formulation, things like that. But what I'm looking at is next level. Of course, T mu nu can explain. So conservation of energy and momentum. So that's where I have problem here. Local conservation may be there, momentum. And they're explaining. See what I'm explaining here. You see that? The Riemann thing. You see this is the Riemann form. This is the Riemann tensor. And how the Riemann tensor.
What's that called again? Where you have the little d there.
Yeah, you see here the Riemann. They convert the Riemann.
You know what's that? What's that thing called again? Where it's like a I've forgotten the name of it, but it's used all the time. Where it's like it's a 4x4 matrix with the Kronecker delta. Is it or something?
Kronecker. Oh yeah,
is that what that is?
Yeah, that's one of them. So this is the way they finally get. You can write this out. This is the Kronecker delta that you're talking about here.
Okay, and then you have the imaginary unit as well, is it? So is that what you're saying? They're splitting it into two different things?
Yeah. Okay. And then they get the Ricci curvature tensor, scalar curvature. Then you can show this one, right? So there's a whole lot of derivation here. That's why I'm putting out this Wikipedia. What I'm showing is a very simplified thing, what I was showing. But this is more what the formalism is, the actual formalism. So now we have these, right? You see that they are bringing it on top, which is like, you can think of this as a rotation. So you can convert this to a spherical coordinate using this from Euclidean to spherical coordinate. Using these, you can convert them. Okay. So they are deriving all sorts of things from here. And finally, you see that you can convert them into this form, because when you have the original Riemann, it talks about the angle. Typically I would think this is an angle. These are angles there, angles coming there, and these are the coordinate systems. So it's a very general form. And
well, why do you say it's an angle when I thought the subscripts and superscripts were indices?
Indices, but the superscript I think can refer to the angle, like I was showing.
It's covariant and contravariant or something. Covariant and contravariant.
Yeah.
So you're going you're going forwards or backwards, or it's a forwards or backwards transformation or something, or else it's or covariant, contravariant, meaning is like
you can split
expanding past the other, or then the relative motion of it being in place and the other thing flowing past it or something.
Yeah, essentially, right? in terms of concept, you can convert all the geometry. Of course,
that would be zero. That would be conserved, wouldn't it? Because it's relative. So it's they're both the same thing. So really, we're not saying we're not saying anything here. This is kind of just maths, right? It's not that interesting, I don't think. Like not putting it down.
But the main thing is, the interesting thing is that all the geometry you can convert to matrices. So in terms of either multiplication of matrices or addition of matrices with proper rank, you can convert all the geometry into that, into the algebra. That's the whole idea.
Say that again. All the algebra into
all the geometry that we see, right? You can convert to matrices in terms of matrix operation, like multiplication of matrices or addition of matrices, but you have to take care of the rank of the matrix. That's where the big thing is. And it could be a little bit of a problem. I mean, it does involve into very, very pesky, complicated equations. So, that's the problem with the algebra, whether we can solve that. But that's what the Ricci tensor is, kind of an assumption. It's a simplification of the Riemann. The Riemann thing is not, Einstein did that first, but he couldn't use it in the physics. But then he converted Ricci tensor. That's why he had to spend like years together to convert. Then his idea struck, I should use Ricci tensor. Around the same time, I think Hilbert also did that. But Einstein jumped on it and he came up with the general theory of relativity using Ricci tensor. So then Schwarzschild simplified Ricci tensor of R mu equal to 0 for vacuum. Then I can solve that Einstein equation. Because people are trying to solve Einstein equation, they couldn't. But Schwarzschild said, I will do this one. Then he put everything into metric separator, and then he separated that into vacuum and all that. Then he could solve the Einstein equation. And that became the big thing because that saw the singularity of black hole, and that black hole itself became the huge physics, right? Now the whole thing, people think it's black hole physics, everything, right? So everything is explained in terms of black hole physics. And then you came the dark matter and all that. And now they think that black hole is part of the dark matter, vice versa. And, all this. Then you have the expansion, which is dark energy and all those things, So they're trying to explain the Schwarzschild metric, in a sense, into physics. So that's essentially what's happening. And now people derived a Newton law of gravity from these, right? Simplified that, Gauss's law of gravity, and things like that. So then they put into Einstein field equation, right? And geodesic equation, convert it into geodesic equation. And now they simplified that this is now same as a classical thing, converted to classical Minkowski metric. So people have done all sorts of reduced to Newtonian counterpart. So they connected the classical physics to relativistic physics through this kind of thing.
Right.
Yeah. And then alpha G, all these things. Now you have to wrap our head around what this superscript subscript means. I'm trying to simplify how you can do the operation, simple way. But it's not simple because people are worked out, and you look at thousands of pages, runs to thousands of pages to figure out. So finally they came up G00 is minus C square minus 2 pi. Then the Einstein equation, time component, and all that. But these are real things, people are done these manipulations. And they show that the stress and energy tensor is rho times C square, right? And the density matrix times the C square.
What's rho though? Is that a rotation or a?
No, rho is density. Like vacuum density, all those things. Yeah, density.
Energy density.
Energy density, yes.
So it's essentially the stress energy tensor.
Yeah, that's what T is.
Times the speed of light squared. So times a scalar.
Yeah.
But it's minus. So does that mean the diagonal is inverted or something?
So it is compressing somehow, right? It's going inwards.
Why would you? Oh, I see. You mean it's the opposite of the other ones? But doesn't it, like, don't physicists switch
opposite of
between?
pressure?
Where does it?
Opposite of.
Oh, yeah. I see what you mean. Yeah. Oh, okay. So why? So does that mean it's anti-gravity then? If it's opposite pressure?
No, it is gravity, right? Pressure. When we say pressure, it goes out. Normally, pressure means it goes out.
Oh.
Right. Normally, when we say pressure,
yes,
there's
true,
a pressure
yeah,
inside.
Yeah, of course, yeah. Okay, so that's
this
fine.
This is opposite of that, which is gravity. It's like gravity. So I think they're trying to figure out.
Oh, okay, I understand. Yeah.
Finally, they define Ricci tensor in terms of the stress and energy tensor in this way. Again, complex thing, right? That's what I'm trying to derive, but it's too complex. So that's why I'm showing this Wikipedia. I'm trying to simplify these things to understand the way, but I think we don't want to lose the correctness. So that's why I want to refer to the Wikipedia. So you don't, I simplify as much as possible to understand the concept. So we can understand. So you can understand from that standpoint how people are deriving these all kinds of things. And finally, derive the Einstein thing, 8 pi g or c or power 4. And the vacuum field. See, this is what Schwarzschild did. R mu equal to 0 for vacuum field, right? Then he solved this one. This is how he started getting the black hole and all of it. Einstein-Maxwell equation. That this you can convert to Maxwellian thing. So the gauge theory starts coming here somewhere. The gauge field and all that. So this is an electromagnetic stress energy tensor, right? And then the cosmological term he adds to that, and you get the conventional relativity theory, Einstein-Maxwell equation, and covariant Maxwell equation, which is something like this. Electromagnetic tensor, okay. That I give. Okay. So this one is again the equate all this. I finally get electromagnetic field potential. Okay. This is one of the basis Poincaré basis for the gauge. Coming out with the gauge thing.
Okay.
Yeah. The linearized EFE, Einstein field equation, and polynomial form, all kinds of things people are done. Okay, that's it. So again, this is uppercase. This is different. This uppercase is connected with something written inverse metric tensor, the form that contains metric tensor polynomial form without its inverse. So this Levi-Civita symbol, inverse of the metric in 4 dimensions, written then multiplying both sides by a suitable power of eliminate from the denominator results in polynomial equation metric tensor. The action from this equation can be written polynomial by suitable. Okay, what does it do? So that's
I don't know.
They're not explained what.
Well, maybe the idea is you have it in a polynomial form because it's
to get Hilbert Einstein action.
Maybe it's easier to work with than a derivative or something.
Yeah, no, to get the action. See, action field, to derive action field, probably you need this one. See, that gives a metric, but it doesn't give the action. But this gives the action. That's what.
See. Well, the action meaning the transformation to itself or something.
Yeah, actually, I also say that in my OJT.
Or the gauge, is it? You mean the action of the gauge?
Yeah. So if you differentiate the derivative, the spatial derivative of the action field is time tensor. So the action and space are connected to time. So space and time, space and time connected through action. They are interconnected. So the space time together, they create action event. That's the idea which I use. So I say that you need time tensor to do that because it cannot be scalar because the space itself cannot be fully defined by scalar thing. If 4-dimensional, you need kind of a Poincare group, all those things. So that's why we had to work together because you work more on that. When you bring the time together with the space, then we have to work with the space-time group. And then,
Well,
hopefully that.
well, maybe there's different terminology for action then because, you have the gauge symmetries starting with an action where you have a kind of a mapping from one system to the other.
So let me put for action. Let me see action. What action is. What does it show action? Action physics.
Yeah, it would be a bit too general to just put the word action, wouldn't it?
Yeah, it doesn't fill up. Okay, physics Wikipedia. Let's see what it does. So, if action is a scalar quantity, describes how the balance of kinetic versus potential energy of a physical system changes with trajectory. Yeah. So let's see an equation here. So S is written. It's also the Lagrangian form. It's written in Lagrangian form. So action is kinetic energy minus the potential energy, and then integrated over time. So then you can write Lagrangian, right? This is Lagrangian. So that's why they write simply action as integral of the Lagrangian, right? This is Lagrangian. Kinetic minus potential is Lagrangian, L, and integrate over time. This is a simple definition of action. Integral, the trajectory has to be bounded in time and space. So the trajectory, let's look at the trajectory. So you have converted to Lagrangian. The action is defined integral, okay. Fixed Q and T, Hamiltonian principle, your saddle points, Lagrangian mechanics, abbreviated function action. So a PI, which is the, I would think that's the momentum.
Yeah, probably.
Momentum, yeah. So you can define in terms of
the first definition you had there. You scroll back up to the first definition.
Summation. Yeah, S naught is P times dq, and then sigma P, this is the summation of the momenta.
Scroll back up to the first equation that you were looking at. The very first one.
This one?
No, the very first one. First one. Yeah, okay, so then it says the action balances kinetic against potential energy. The kinetic, for a trajectory of a baseball moving in the air on Earth, the action is defined between 2 points in time, T1 and T2. Okay, so yeah, I think there's so that could be a kind of a gauge and then, or something, and then depending on what system you're looking at, and then I guess there's probably different definitions overall, but it wouldn't have to be a Lagrangian. Like you could, you could always work that in, I suppose, but you could have a mapping from one curvature to another, and that would be there'd be an action there.
Yeah.
So
that's what they're doing here. You see,
but if you're doing right, that would be correct. And then, so if you're saying, I don't know what was your original definition? Something to do with space and time. So you were mapping.
Yeah, you can convert to space and time. Yes. because we are trajectory, right? The action is the trajectory is the space time. So the action is along the space time. So we can connect that in space and time with the,
Okay.
you know,
So, but what does that tell us? Or is that's just a matter of fact? You're just stating
yeah,
something. Okay, but for what reason? Like, what are we getting out of the point or what point
yeah.
were you trying to
So
make?
action can be converted to a field, like a Maxwell a field, right? Electromagnetic field, things like that, can be
Yes.
connected to action through the gauge equation, the gauge field. Uh, so let me see whether there's a connection here, or we'll put it gauge field and the action. Let's see whether they have it here. So classical fields to obtain equation of motion. Electromagnetic field is connected with the action, gravitational field. So let's see how they're deriving it. Maybe we need another one. Uh, how is action linked to electromagnetic gauge fields? Something like that. People are school stuff. Gauge theory. So that brings to gauge theory. I think they made it. Let me see whether they describe that. Field theory, Lagrangian, talks about invariance. Another 5 minutes will knock it off, but uh, let's see whether they talk about here somewhere. Global symmetry, local symmetry, gauge fields. This all does description. Okay. So classical electromagnetism, delta V is the gradient of the potential, right? Yeah, right. Minus del A over vector potential A, del over del T. So this is a Maxwell equation. The gauge become not just so A to A. So you convert this to make it a gauge, scalar gauge theory. So you get this stuff, scalar gauge theory convert. So now S in this case should be action, isn't it? What is S
Probably.
here?
Yeah. Action
Then
for. Oh, wait
should
a
be
second.
action, right?
Some usual action. So for each scalar field.
The usual action for each scalar.
Yeah.
Okay. You see that? So the action is used,
So
but
the
in a
action is
slightly
in there
different
in
way.
the brackets, I guess.
Yeah.
In the big
So it
no,
is
not
used
in
in
the
a
big
very,
brackets. 1/2 minus this. The action there is a kind of a Lagrangian, isn't it? Because you got 1/2
isn't it
m.
the same as a Lagrangian? Yeah.
Okay.
Yeah, this is a Lagrangian form. So they are converting it into, I have to understand. Lagrangian invariant. Okay. Is invariant under transformation. So this they're making it invariance to bring out the invariance. That's the main thing, gauge theory, right? The invariance.
Yes.
Uh,
Symmetries and of
so
course
then
the
you can connect to group
conservation.
structure. Yeah, group structure, group, and using Noether's theorem,
Yeah.
G matrices. So then you can use your space-time group and all eventually, I think, using that. That's the idea. So
Okay.
gauge covariant derivative
Mm.
here, gauge field. So this transformation of the gauge field should be like this. Element of Lie algebra. So they bring in the Lie algebra.
Yeah.
Locally gauge invariant Lagrangian. So locally you can create a invariant called the
Okay.
gauge transformation. That you also use it, right? Gauge transformation. A is
Yeah.
called the gauge transformation. So then, and the original globally gauge invariant is to be interaction Lagrangian. So Feynman diagram comes there automatically. Bosons, the gauge boson and things like that. They connect
I
that.
tend not to use any of this kind of mathematics. I find it a little bit.
Yeah.
It seems a
Too
little
complex,
bit.
right?
I'm still struggling to understand what this nu mu f mu nu thing. I know it's to do with electromagnetism. Oh, this is Yang-Mills, Lagrangian for the gauge field. The picture of
That's
classical gauge theory developed in the previous section. Is
so
this
now,
is this the Yang-Mills gauge or something?
Yang-Mills action finally.
Is this used in? Is this for?
Yeah.
Is this not for the weak interaction, or is this something else?
I think it's string theory uses this. String theory uses this somehow.
I think though there's an issue with it. It doesn't. See, there's something with the name Yang-Mills, and it's probably used in string theory, but it's also to do with the weak interaction.
Yeah, probably.
It's not a full theory, you know. It's just like
no
thing.
Then the Dirac comes there. The action is written in terms of Dirac also, Dirac equation.
Right.
And then that brings the quantum aspects, localizing the symmetry and all that.
Yeah. Okay.
So there are a lot of things here.
Yeah.
Feynman's quantum electrodynamics connect with these things. This is how they come up with theory of everything. Finally, you know, they use all this stuff, put them together, mix them together, and they come up with the theory of everything. Yeah.
Well,
so it's a derivation. They're all derivations. Another few minutes will knock it off. But so Yang-Mills now is given this one, and they use all kinds of strange things. They use square root of G and all that somehow comes into picture somewhere. It's about pure gauge. So this is a pure gauge transformation. The pure gauge is just the set of field configuration. This is used quite a lot. Final this thing. Gauge orbit. Wow. So lower subscript, upper subscript, you know, you can move it using covariant and also metrics. You can convert a lower metric, the subscript to superscript using metric.
Is it the Jacobian or something like that? The Jacobian transformation.
This is the electroweak theory that you are talking about, I think.
Yeah. If you click on that, you'll see if Yang-Mills is in there. It might be a different Yang-Mills thing. I don't see it there so far. I'm sure it's in there
Big Bang.
You'd have to scroll down a bit. Formulation. Keep going.
SU2, SU1, right? Isospin.
Yeah.
That you are dealing with this stuff.
It's just degree. Yeah. I'm dealing with it from a different perspective, though, just based on the, what do you call those groups again? Well, group theory.
Group theory.
Yeah. Maybe, no, is it the Yukawa coupling or something up there?
Yeah, it could be that. Yeah, Yukawa.
I think it is Yang-Mills.
I think Yukawa coupling comes there.
Yeah, and so I actually was watching a Q&A with Sean Carroll as well, and he doesn't really go into group theory that much, but he did something that I found very interesting and useful that I would have to apply to my own work done before, you know, to see how it affects because it's all about commutation. So if you have two matrices and they commute, well, it's something to do with that anyway. If they're non-commutative, then that means those two fields don't interact or something, you know?
Oh yeah. So, that's true. They decouple or decouple based on the coupling constants, things like that. That's why the Yukawa interaction there.
Yeah, so that's one element that in my own research that I never I mean, it was so obvious. It was there from the start, but I guess I was so focused on other aspects of the model that I never kind of set that out in stone to begin with. So I might sit down and do that at a later stage, which could kind of reorder everything. Or if it doesn't do that, it would like just disprove the whole model. Or else it would say, well, this model has nothing to do with what they're normally using gauge or group theory for. So it sits entirely separate and may not even be that useful, which would be a kind of disproving. But I'm not really in any hurry to do that because, you know, I've kind of moved into the cosmology side of things anyway. So, I mean, another idea I was thinking about there earlier is like, imagine if the dark energy force that we were talking about with the cosmological constant is actually in some way a structural side effect of the hypersphere being a finite sphere. So, you know, the way we were talking about a bubble of water that has a surface tension, and that surface tension kind of works against gravity to keep the bubble in a bubble state, you know, it doesn't collapse. So then
it's not Marangoni, right? It's not Marangoni effect, right?
No, it wouldn't be. It would be more of a surface tension effect, right? So I don't know what there's other names for that, but so then you could think about maybe that force is or even just the bubble itself, like just the structure of the bubble and the nature of what it is made out of, the space-time has an elasticity to it, or a cohesiveness, I mean, and that cohesiveness is the thing that prevents it from collapsing. So that would be, so dark energy is essentially the structure of the universe, or the cohesiveness of space-time at certain scales. But then at other scales, it would begin to break down. That's where you get your kind of continuity and other aspects.
So
but
don't need
there's quite a bit of work to be done before we get to that point, and there's also some very weird aspects to it that.
So we don't need a cosmological constant.
Well, you could say it's there, but it's like it would be equivalent to talking about maybe the value for surface tension, you know, or something like, or why does the water have a round structure? You know, oh, it's because it's in a glass. The glass is round. It's kind of just borrowed from the thing that's already like the geometry of the universe. Something like that could be an interesting.
It's very small. Cosmological like 10 to the power minus 52 or something.
Yeah, and this is number. It's small, so it'd be interesting to see how that would fit in. But also, we found that I remember through the calculations I did with the Marangoni flow catastrophe that the dark energy cosmological constant, or just the cosmological constant in general, doesn't fit with the equation for the Marangoni flow catastrophe, and we needed the 0 point energy instead. So if the cosmological constant is just a kind of a holdover, if you like, from the structure of the universe, and is not really a real value, is not really a real force, then that would explain that. We wouldn't need to worry about it. Doesn't mean that we'd have to remove it from any equations, because it would still be like a fictitious force, or, you know, it would still need to be, it could still be accounted for without any problem, I don't think. Just like the way we say that gravity isn't a real force, it's a curvature, it's a geometric thing, but we still have to account for it with equations and different factors. Therefore, we could do the same thing with the cosmological constant. It's not really real, but it's just based on the geometry of the hypersphere, so we can account for it with this value, but we don't really need it. So that could be something that's useful.
I think we are almost done. I had to start. So we'll continue a couple of weeks, right? 29 most likely. We
Yeah.
can get back to our the things,
Sure. Okay, that
and
sounds
then
good.
we will yeah.
Okay, so we'll leave it there, and
Okay,
okay, I'll just close it
thanks a
down.
lot. Have a great time at your conference and Portugal, and let's know the proceeding. What happened? We'll talk about that when you come back.